Let's take a look at example 3. In example 3 from section 4.4, we want to solve the differential equation y double prime minus 2y prime minus 3y equals to 4x minus 5 plus 6x e to the 2x. So we'll go ahead and again we'll solve for the complementary function first. So we want to find y sub c. So we're going to solve the associated homogeneous differential equation y double prime minus 2y prime minus 3y equals to 0. The auxiliary equation is m squared minus 2m minus 3 equals to 0. This is solved easily via factoring. This factors as m minus 3 times m plus 1 equals to 0. Set each factor equal to 0. And we're in the case where we get two distinct real roots. We have m equals to 3 and m equals to negative 1. Therefore, the complementary solution is going to be y equals, we have c1, it will be e to the 3x plus c2 e to the negative x. So we've gone ahead, we found our complementary solution. Now let's go ahead and find the particular solution. And again, just to kind of save some space, let me go ahead and write the complementary solution up here, just so we can look back at it later. So to find y sub p, we want to take a look at this function g of x in this case. And the entire function g of x, if we kind of break it down, it's made up of a couple of different pieces. Okay, so let's kind of think about the y particular as being maybe itself a couple pieces as well. Okay. The first part of it, if we look at this 4x minus 5, that's a linear polynomial. So it makes sense that a linear polynomial of the form ax plus b would also be part of our particular solution. And then we have the second piece here, which is 6x times e to the 2x. And we want to make the following observation. So we know that with this particular differential equation, we need the original function y, y prime, and y double prime. Same thing when we take yp, or in this case yp2, when we take its derivatives. Notice the following thing though. If I take the derivative of 6x e to the 2x, this would involve the product rule. It's 6x times e to the 2x. Its derivative would be 6 e to the 2x plus 6x times e to the 2x times the chain rule times 2, which would give us 6 e to the 2x plus 12x e to the 2x. And the point that I'm trying to make here by calculating just the first derivative of this kind of piece is that notice we get something that looks just like it. We get a 12x e to the 2x. So it's an x e to the 2x term, but we also get, in essence, a constant times e to the 2x too. I'm not going to show the work for this, but if you were to go ahead and take the second derivative or the derivative of this expression, you would again end up getting two terms. You would get one term, which would be like a c e to the 2x. It would be some constant times e to the 2x. And then you would have something else, which would be like a d times x e to the 2x. So with that in mind, it looks like the second part of our particular solution is going to have terms of the following type. It makes sense that it might contain things like c e to the 2x plus d x e to the 2x. And then according to the superposition principle, or just the way that this works, that yp, if both of those are solutions, then our particular solution in this case is going to look like the following. It's going to be ax plus b plus c e to the 2x plus dx e to the 2x. And now our goal is to try to go ahead and see if we can solve for a, b, c, and d. To plug it into this differential equation, we need both the first and the second derivative. So let's go ahead and find those. Y prime p would be equal to a, the derivative of ax is a, derivative of a constant is 0. The derivative of c e to the 2x, you're going to have to use the chain rule there. You'll have a 2 that will come out multiplying. You're going to get 2c e to the 2x, plus, as we saw a moment ago, to do the derivative of this piece, that's going to be a product rule. The derivative of dx is d. Leave the e to the 2x alone. And now plus, leave the dx alone. The derivative of e to the x is 2x times 2. So y p prime is going to be equal to, we have a plus, these two, if you look at these are the same term. So I'm just going to kind of combine them. 2c plus d. You're just essentially factoring out the e to the 2x from them. And then this is going to produce 2dx e to the 2x. We also need the second derivative, so y p double prime is going to be equal to the derivative of a constant is 0. This is a constant times e to the 2x. You're going to get 2c plus d, leave the constant alone. The derivative of e to the 2x is e to the 2x. And then from the chain rule times 2. Plus, and now here again we have a product rule when we differentiate this piece. The derivative of 2dx is going to be 2d. Leave the e to the 2x alone. And then plus, now we leave the 2dx alone. The derivative of e to the 2x is e to the 2x times 2. So we have the following. Y p double prime is equal to, I'm going to distribute the 2 in here. That gives us a 4c plus 2d e to the 2x. This is a plus 2d e to the 2x plus 4d x e to the 2x. And we can do it one better because these two are both e to the 2x terms. So we can add those coefficients. And we get that y p double prime is going to be a 4c. 2d plus 2d will give us 4d e to the 2x plus 4dx e to the 2x. Now that we have that, this is our second step. We're going to plug this into the differential equation. So y double prime, that's this thing down below. That's 4c plus 4d e to the 2x plus 4dx e to the 2x minus 2 times y prime. Y prime is this thing here. I hate to have to erase all of this, but we're going to have to erase a lot of it just so we can squeeze things in. Let me at least write the form of yp up here so we remember what each term these coefficients go with at the end. We said ax plus b plus c e to the 2x plus dx e to the 2x. Okay. So we're right here. This is minus twice y prime. Y prime is this thing here. So that's a plus 2c plus d e to the 2x plus 2 dx e to the 2x, a lot of writing here, minus 3 times y, p. P is this thing here. That's 3 times ax plus b plus c e to the 2x plus dx e to the 2x. And this is going to be equal to, the right hand side is 4x minus 5 plus 6x e to the 2x. Okay, so we have it plugged into our differential equation. We're going to eliminate the parentheses, and then we're going to group like terms. So on this left-hand side, we have 4c, 4d e to the 2x. Not these parentheses, but the ones that come from distributing these coefficients in here. Those are the ones we're going to eliminate. You could do more if you wanted to, but I'm trying to keep things nice and tidy until the end. This negative 2 needs to be distributed, so let's go ahead and do that. We get a negative 2a, and now I'm just going to go ahead and put it directly into this coefficient. So this will be plus negative 2 times 2c is a negative 4c, negative 2 times d is a negative 2d, e to the 2x, negative 2 times negative 2 will be a negative 4dx e to the 2x. And then distributing negative 3 into here, we get negative 3ax minus 3b minus 3c e to the 2x minus 3dx e to the 2x. I'm just going to be a little bit lazy here. Is equal to that thing. So as we saw a moment ago, we want to kind of rewrite this left-hand side by factoring out like terms, and I'm trying to set it equal to this thing here. So with my left-hand side, let me plop out and pluck out the polynomial part first. So the x term, like I have on the right-hand side, it's going to be this term right here. This is my only x term on the left-hand side, so I'll put that first. It's negative 3ax. Now let me look for the constant term. There's a negative 2a term and a negative 3b term. Those are the only constants. So negative 2a minus 3b is that constant term. The next term I have on the right-hand side, well, I don't actually have it here, but I probably would have written the next had it existed, would have been like a constant times e to the 2x. Where are our constant times e to the 2x terms? Well, there's one right here. Here's another one. And there's one more right here. That's another e to the 2x term. So I'm going to try to do a little bit of arithmetic to save us some space and some writing here. But let's combine those coefficients in the e to the 2x. So first of all, a positive 4c and a negative 4c, those two cancel. 4d and a negative 2d would give us a positive 2d. And then we also have another negative 3c here. So we have a negative 3c minus 2d. And that's times our e to the 2x. And now whatever is left over should be the x e to the 2x type terms. We have a 4d, a negative 4d, and then from over here we have a negative 3d. So the 4d and the negative 4d cancel, and so what we get is simply just negative 3d x e to the 2x, and this is supposed to be equal to that g of x, which was 4x minus 5 plus, again, you don't have to do this. I'm going to do it just because I think it helps some students. I don't have any e to the 2x term, so I can put it with a coefficient of 0. And then we also have a plus, it's a 6x e to the 2x term. And now we're going to go ahead, our system of equations to solve for a, b, and c is going to come from equating the coefficients. For this equality to hold, so the equality right here, think of this as the equality of functions. So for those two functions to be equal, I need the constant coefficients to match up. So where was my x terms at? So I'm looking at the wrong color. I'm gonna try to color code this as best as I can. We only had one that was in yellow. The x term on the left-hand side has a coefficient of negative 3a. The x term on the right-hand side has a coefficient of 4. Therefore, equating those two coefficients will tell us that negative 3a is equal to 4. Let's now compare and equate the constant coefficients. If I equate the constant coefficients, then we see that the negative 2a minus 3b, that's the constant on the left-hand side, has to be equal to the constant on the right-hand side. Therefore, negative 2a minus 3b has to be equal to negative 5. So we were equating those linear coefficients as with the constants. So we said that negative 2a minus 3b had to be equal to negative 5. If we now compare the coefficient of the e to the 2x terms, that means that negative 3c minus 2d will have to be equal to 0. And then lastly, by comparing the coefficients of the x e to the 2x terms, we see that negative 3d will have to be equal to positive 6. So what we end up with, we have 1, 2, 3, 4 equations in 4 unknown variables, those variables being a, b, c, and d. And we immediately get some information. The first equation, you can divide both sides by negative 3, and that will tell us that a is going to be negative 4/3. The last equation, you can simply divide by negative 3, and that will tell us that d is going to be negative 2. We can take this value of a and plug it into the second equation to solve for b. Negative 2 times times a, which is negative 4/3, minus 3 times b should be equal to negative 5. That's going to be positive 8/3 minus 3b equals to negative 5. We would now go ahead and subtract 8/3 from both sides. So negative 5 minus 8/3. If we do that, that would give us negative 23/3. And then from here, you could divide by negative 3 or multiply by negative 1/3. And we would find that b would be equal to a positive 23/9. So b is positive 23/9. And then if we take d and we plug it into this equation, the third one, we can solve for c. We have negative 3c minus twice d, where d is negative 2, should be equal to 0. Negative 3c plus 4 equals to 0. Subtract 4 from both sides, and then divide both sides by negative 3, and we will get that c equals 2 to 4/3. So we've now solved for our particular solution. We have a value of a, b, and c. So we now know the following. Our y particular which I had kind of highlighted the form over here. So y particular is equal to ax, that is negative 4/3 x, plus b, that's plus 23/9, plus c is 4/3 e to the 2x, and then plus d, where d is negative 2x e to the 2x. And that gives us the particular solution to our differential equation. Again, notice the little bit of subtlety that sometimes gets lost when you're trying to guess the form of y sub p. It was wise of us to assume the ce to the 2x part was part of the solution, because we do get a 4/3 e to the 2x as part of y sub p. And again, we started that at the beginning of the video, and we investigated it. When you take the derivative of the term that does appear, that x e to the 2x, when you start doing things like first and second derivatives, things like a constant times e to the 2x pop up, and therefore when we assumed our particular solution, it made sense to include a constant times an e to the 2x term. Let's go ahead and summarize it. Again, the general solution is going to be the complementary solution plus the particular solution. The complementary solution was the solution to the homogeneous differential equation. That was c1 e to the 3x plus c2 e to the negative x, and then plus our particular solution, which is negative 4/3 x plus 23/9 plus 4/3 e to the 2x minus 2x e to the 2x. And there you have it. That's the general solution to this differential equation.